Hello, my name is Lucas Rostowski. I'm going to be speaking to you today about a silicon photonic evanescent field sensor architecture using a fixed wavelength laser. This has been a large team effort combining the University of British Columbia, McGill University, and Laval University. First, let me tell you how this project came about. So in March 2020, right at the beginning of the pandemic, I was approached by Gemina Labs, and they are developing a non-invasive testing for COVID-19 using saliva samples with dual affinity immunoprobes in a lateral flow assay. They approached me and they were interested in multiplex silicon photonic sensors, which is what we've been working on. And we have a SPIE Fab consortium, which is focused on fabrication of these types of chips. So many of us got together, students, postdocs, staff, professors, industry, and we started asking ourselves, could we develop a low-cost biosensor architecture? And what I'm presenting today is the result of the past year work in this effort. So the overview for the presentation is I'm going to start with discussions on rapid point-of-care testing, talk about how evanescent field sensors work and some commercial state-of-the-art. Then I'll present to you the fixed wavelength DFB laser architecture, which is multiplexed, and talk about performance metrics for silicon photonic resonator systems. Then I'll go into how we integrate the laser with silicon photonics using photonic wire bonds, a little bit of thoughts on microfluidics, electronics, and next steps and opportunities. So what we found recently is that medical testing outside of the clinic is the new normal. COVID-19 has certainly exposed this and increased our interest in medical testing. And there are many other applications for rapid testing at home and at work. So how does an evanescent field sensor work? So we start with taking a look at the cellular environment where you have a cell, and on the outside of the cell you have toxins and viruses that bind to the cell. And so in order to make detection of these viruses and antibodies and so on, we can replace the cell with some sort of sensor surface. And in our case, we're going to be working on silicon. And so then you need to provide a stimulus, in our case a laser, and then the response, we're going to be using a detector to measure this. So the gold standard for these types of evanescent field sensors is the surface plasmon resonance technique. So there are several companies that have built products out of these, and these are generally systems that are relatively large and they're used for lab experiments. Now, there's a company, Genolite, that for the past 10 years or so has been commercializing silicon photonic sensors. And early on in the pandemic, they managed to demonstrate sensors for COVID-19, and they presently have a panel with a variety of antibodies for COVID-19 and MERS, influenza, and other things. So this is taking advantage of silicon photonics, very low-cost chips. You can manufacture these in high volumes. And the system that they have can handle on the order of 250 patients per day, and it's a multiplex sensor, so you can measure multiple things. So some of the problems with this architecture are that you require a tunable laser, and you need to couple the light from the laser into the silicon photonic chip, and that's really expensive. But let's talk about how the ring resonator sensor works. So you have a ring resonator with a waveguide that's exposed to the fluid, and particles, say antibodies or viruses, bind to the surface of the silicon, and you're measuring a change in the effective index of the waveguide, which is evident via the resonance frequency shift. And so in the plot on the far right, you can see essentially repeated optical spectral measurements with a tunable laser, where you're doing many, many sweeps, and then you're curve fitting the spectrum, extracting the peak, and tracking how this peak evolves over time. And from that, you can get information about the binding of these antigens to your sensor surface, both transient and steady state effects. So our proposed structure is to try to work towards having portable, low-cost sensors. And so we want to put as much intelligence as possible into the sensor chip. And so what that means is that, of course, we have the silicon photonic sensor, in our case, a resonator using sub-wavelength structures. But on the chip, we're also going to put the DFB laser, the microfluidics, the tunable detector, and control electronics. And so all that would go on a small chip. Therefore, it has a very small form factor, and it could potentially connect to a smartphone. The idea of this would be that results would be obtainable in minutes. You'd be able to do a lot of multiplexing capability, and the silicon photonic chips and the lasers are low cost at high volume, and this whole sensor, being a medical device, would be disposable. So let's compare the standard approach like Genelite is doing, where you have a swept tunable laser. Let's assume the laser costs about $10,000. On top of that, you also have to have some mechanical steering, nanopositioners or galvanometers to align the laser beam to the chip and then to collect the light out of the chip into a detection system. And so this means that this is a lab benchtop instrumentation. In our approach, we're putting the laser on the chip, and so the laser costs on the order of $1. The silicon photonic chip is on the order of $1. And so we think that this will be a lower cost solution. So the way we integrate the laser with the silicon photonic chip is by creating deep trench pockets in the silicon, and then pick and placing the laser into that hole, and then using photonic wire bonds to connect the DFB laser into the silicon photonic chip. On the silicon photonic chip, there will be, in our initial design, 16 sensors that are sub-wavelength waveguides that have high sensitivity. And we have 3 designs so far. The one I'll be discussing today is with Applied Nanotools, and we also have designs for SUNY AIM Photonics and Global Foundries. So a little bit of a comparison to other technologies out there. ELISA is probably the most accurate instrumentation that's used. However, there are some disadvantages. It's expensive, it's only in the lab, and it takes a long time to get results from these systems. SPR systems, I've talked about, that's another alternative. Again, benchtop, commercial silicon photonics system, benchtop. And so where we're proposing is the system would not require labels. It would be handheld, portable, it would be multiplexed, provide quantitative results, and presumably results on a similar time frame as the Genelite, so under 20 minutes. And the big differentiation would be the unit cost of the sensor. We anticipate it would be on the order of $20 or $30. Let's discuss some of the performance metrics for silicon photonics sensors, and specifically I want to focus this talk on resonator sensors. So the first easiest one to define is what's called the bulk sensitivity. So this is the change of the wavelength of the resonator as a function of the change of the cladding material, or the water or salt or whatever is on the outside of the waveguide. And so this is very easy to quantify in the lab. You can do, for example, isopropanol alcohol or salt, and then from that you can get this bulk sensitivity. More important is the surface sensitivity, so you can do experiments by doing monolayers of different chemicals being absorbed to the surface, and then essentially doing step layer by layer deposition and quantifying the surface sensitivity. One of the most important figures of merit is the limit of detection, and specifically the system limit of detection. And so one way to quantify that is to look at how strong your signal is and compare that to how small your noise is. And so in the bottom picture, you see essentially measurement over a time series, that there are variations in the central wavelength, and those could be from electronics and thermal fluctuations and so on. And so that's the noise, and then the signal is what you see above that. And so our limit of detection will be the smallest index of refraction change or surface sensitivity that you can measure. Thinking about the 2 factors that go into this limit of detection, there's the waveguide sensitivity and there's the architectural sensitivity. So on the waveguide side, we have various types of waveguides that can be used to detect these index changes. And the starting point might be a rib or a strip waveguide. There's been lots of experiments with slot waveguides, and the one that has the highest sensitivity is the sub-wavelength waveguide, because a lot of the light is traveling outside of the silicon, and you also have a lot of surface area on the waveguide, and so there's a lot of locations for binding to take place. In terms of sensing architectures, there's 2 choices that are pretty common. One is the Mach-Zehnder interferometer, or various types of interferometers. and the other one is some sort of resonator, and rings are the ones I'll be talking about. These two, interferometers and ring resonators, are somewhat challenging to compare, but I think the feeling is that they have similar intrinsic sensitivities, and so it makes sense to pursue both approaches. So sub-wavelength waveguides, I mentioned, have a very high sensitivity, on the order of close to 500 nanometers per refractive index unit. And you can see the results here for calibrating using SALT, and also doing some simple experiments. So these were results from 2016 on ring resonators. Now, thinking about the intrinsic limit of detection for ring resonators, or any resonator for that matter, first we talked about the system limit of detection, and that's going to be limited by instrumentation and many other things beyond just the resonator itself. And so to make it easier to compare different types of sensors, we use an alternative figure of merit, which is the bulk intrinsic limit of detection. And it's very simple to quantify and calculate the minimum detectable change in your index delta n. And the way you think of this is that it's defined as how much delta n is required to shift the resonator by a full line width. And so you've got one bump, another bump, and you're shifting a full line width. So the intrinsic limit of detection is much larger than you would actually do in a system, because you can curve fit the spectrum and extract a much smaller delta n. But it still is useful as a comparison between different types of sensors. And so the intrinsic limit of detection is, you can calculate as the wavelength divided by the quality factor and the sensitivity, in this case the bulk sensitivity. And what you can see is there's a trade-off in this equation, that you can get a higher quality factor or a higher sensitivity waveguide to achieve the same intrinsic limit of detection. So we've done a survey here that shows you this trade-off between sensitivity on the y-axis and the quality factor on the x-axis. And you can see that there's been lots of experiments with various types of geometry, slot waveguides and rings and disks, Bragg grating, sub-wavelength, and so on. And also different wavelengths. So a lot of experiments have been done at 1550, but there's also been experiments at 1310. And you can see that there's a consensus from all these experiments that somewhere in the 10 to the minus 4, close to 10 to the minus 5, is where the limits are for the experiments so far. And the work that I'm presenting today is very close to the best in terms of performance. So you can see that we're on the right-hand side of the plot in terms of the intrinsic limit of detection. So what are the limitations for the intrinsic limit of detection? Water is the biggest culprit. And so if we're working on saliva or blood, water absorption is the fundamental limitation. And to think about that, imagine where you have a waveguide that has a very high sensitivity. That means the light is traveling in the water, so you have higher absorption, therefore your quality factor is reduced. And so that's where this trade-off comes in between Q and S. Now, 1.3 microns has a lower water absorption than 1.5 microns. That explains why you can get better performance. Now, by the time you get to 1.3 microns, the designs are starting to become limited not by water, but by waveguide loss. And so you may also wonder, can you do better by going to visible wavelengths? And I suspect you're not going to get much better improvement because the waveguide loss becomes the limiting factor, and waveguide losses are not going to be dramatically better at the visible wavelengths than in the near IR. So let me describe a little bit about the details of our design. So the first is the wavelength. We're using 1.27 microns, which happens to be the minimum water absorption in this wavelength range. And it also happens to be a wavelength that's readily available in DFB lasers. We're using sub-wavelength grating waveguides, which maximize the waveguide sensitivity. And we're using this fishbone structure, which is less risky for foundry manufacturing, and yet it has a similar sensitivity as regular sub-wavelength waveguides. So the plot on the right shows the quality factor from the spectrum, and the sensitivity was calculated, and we get a calculated calculated/measured intrinsic limit of detection of 4 times 10 to the minus 4, and that is near the fundamental limits that I described on the previous slide. The fabrication for this device was done by Applied Nanotools. So let's talk a little bit about silicon photonic chip fabrication. I'd like to introduce to you the SPIE Fab Consortium. So this is a group of companies and universities that have gotten together with government grants to accelerate silicon photonic fabrication and development cycles. And we have a lot of different applications that we're pursuing, but this consortium is what enabled this work to go on. Now, SPIE Fab is doing prototype fabrication, and this means that once we validate our design, we can translate the design to low-volume research foundries and eventually to high-volume manufacturing. And the designs that we're pursuing are compatible with all 3 levels, all the way from high volume all the way down to the rapid prototyping. So at UBC, the facility that we have for silicon photonics fabrication, the 2 key pieces for the work I'm describing today are the electron beam lithography system, which has been operational now for almost 3 years, and it can fabricate up to 200 millimeter wafers, and a recently purchased tool from Vanguard, which is a photonic wire bond tool. So next, let's talk about how we integrate the lasers using photonic wire bonding. So photonic wire bonding is a new technique for packaging, and it achieves low insertion loss, and you can have free-form connections between different optical components. So this is useful to make connections between silicon photonic chips and other silicon photonic chips, or fiber arrays, laser sources, and other types of optical amplifiers such as SOAs, and to silicon photonic chips. The way this works, it's a 3D printing that is based on a femtosecond laser that leads to 2-photon polymerization to write low-loss waveguides, and it has a very high accuracy, placement accuracy. So these wire bonds are written very well aligned to the waveguides, the laser, the optical fiber. And they're compact and mechanically stable, and potentially could lead to fabrication of millions of units. And so for testing, what's really nice about this is that we can assemble these and prototype and test them all in a day. And we don't need any active alignment to couple the light into our silicon photonic chips. We just place the laser, write the wire bond, and then we have a system working. So this is an easy approach to plug it in and test it. And it also allows us to build systems that have multiple types of chips, such as 3-5 semiconductors with silicon chips. So how this works is we place the silicon chip and the laser on some kind of carrier and maybe in the optical fiber. You drop the photoresist on top of the assembly. There is software that performs image recognition to find where all the waveguides are. It performs a calculation of the waveguides, and then it writes using this 2-photon polymerization approach. It exposes the photoresist and solidifies the polymer. Then you develop it, which washes away everything except for the photonic wire bond. And then finally, you cover this with a cladding to encapsulate and make the photonic wire bond robust. So the approach for integrating lasers on our chips is we are recessing a cavity in a silicon wafer. So this gets rid of the silicon dioxide, buried oxide. It goes down into the handle, so you have good thermal conductivity. We make sure that the bottom of the cavity is metallized because the lasers have a backside contact. We place the laser. Presently, we're doing it by hand, but that could be done by pick and place. And then you perform the electrical wire bond and the photonic wire bond, and then you cover it up with this with the cladding for the photonic wire bond and for mechanical protection. And so the recessing is also useful because it allows us to make sure that we're matching the height of the laser to the photonic wire bond, and that results in shorter photonic wire bonds, less curvature, and faster writing time. So here's some initial pictures of some of the lasers that were placed on these cavities. The lasers, as I mentioned, were these fixed wavelength 1.3 micron lasers. that are about $1 in volume, and there's multiple lasers that multiple vendors that make these lasers, and so we verified that this approach, the lasers survive in this approach, and in terms of soldering for photonic wire bonding. So here's some experiments of taking these lasers. In order to develop the process for photonic wire bonding, the easiest way to proceed is to couple the light from the laser into an optical fiber. And so these are results here showing light from a DFB laser coupled into an optical fiber. There was 6 experiments that were done, and you can see the coupling efficiency. It went from 0% coupling efficiency up to 66% coupling. So that's from DFB into a single mode fiber. And you can see that the optical spectrum and the Li curves remain excellent after the photonic wire bonding. So it doesn't look like there are problems with feedback, and there's no degradation in the side mode suppression ratio. So in terms of fine-tuning the position, that's important. That's done on the software side. So you have to optimize for where you want the photonic wire bond to be written. And so there's a vertical adjustment and also mode field diameter adjustment that's done. Now, how would this work for high volume applications? The idea is to place a wafer, say a 200 millimeter wafer, in the machine, and pick and place the lasers. So in a 200 millimeter wafer, you can get on the order of 3,000 chips, assuming the die size is about 2 by 4 millimeters. And so you'd pick and place those 3,000 lasers, and then cover it with photoresist, put it in the machine, and the machine takes about, or it has the potential to take about 10 seconds per die to write all these things. And then you would do all the dicing and subsequent fabrication steps. So next opportunities and challenges and steps for this project. So first, there's a lot of other applications beyond COVID-19. So lots of different infectious diseases and biomarkers for things like arthritis and Alzheimer's and cancer, general wellness monitoring. So that's in a biological space. And then the non-biological things like water quality monitoring and industrial sensing. So many applications, and you can imagine that these kind of small chips could find their way in a variety of industrial and medical applications. There's a company in Boston called SiFox. They're pursuing a similar goal of making this small form factor biosensing chip. So it's exciting to see that silicon photonics could play a big role in at-home and point-of-care diagnostics and sensing. Speaking about microfluidics, so microfluidics is a big challenge to try to get these to these low costs that I was describing at the beginning. We are presently doing microfluidics designed for university experiments. And so one of the next steps for this project is to investigate how you can achieve high volume microfluidics to deliver the reagents to these chips. Another part is the electronics. And so we're using benchtop equipment, which again is suitable for university experiments, but we will need to develop high volume CMOS electronics for controlling the laser and the sensor, for signal processing, and to interface to a mobile device. So concluding remarks, so silicon photonic sensors were first commercialized by Genelite. Most of the silicon photonic sensors to date have been based on passive optical chips, which require costly and bulky instrumentation. So they don't take advantage of the inherent strengths of silicon photonics, which is all about integration. Silicon photonic circuits have the potential for integrating all the photonic and all the electronic functionality on the chip. So we should think about taking advantage of that, and that should reduce the bill of materials for the sensor systems and could lead to a potential for a complete disposable sensor system on a chip. There remain several challenges in commercializing such silicon photonic biosensors based on this fixed wavelength sensor approach. And there's a few that I list. So the first is limit of detection. So this is not only dependent on the biosensor transducer that I talked about. So there's this intrinsic limit of detection, which I think we're doing pretty well on that figure of merit. But there's also sample collection, sample preparation. All the chemistry has to do a really good job at binding and being specific. So functionalizing the sensor surface. High specificity is also important, so making sure that we have a low false positive rate. And one solution that Silicon Photonics offers is that because we are able to multiplex many different types of chemistries and biomarkers, then you can get multidimensional data, and that allows you to essentially validate and have more confidence in your answer that, indeed you have COVID-19 versus influenza. In terms of cost, we've talked about major cost reductions in this talk, which is the tunable laser, the swept tunable laser. So it's not just an ITLA, but it's a swept ITLA, and replacing that with a low-cost DFB laser. And we also talked about optical alignment and nanopositioners, and so we eliminate that using these photonic wire bonds, and so now we're taking maybe 10 seconds to write these photonic wire bonds. The next steps, as I described, microfluidics, that is going to take some work. CMOS will take work, but that's already in a manufacturable silicon process. So solving these problems should enable small form factor silicon sensor systems, and this tight integration of all the functionality I think is one of the key strengths of Silicon Photonics. So if we can get lasers with photonics, electronics, microfluidics, and chemistry all in one chip, that would be extremely exciting. If you want to keep in touch with us, so SPIE Fab, as I mentioned, is this prototyping foundry. We have two branches. We have the educational branch, which is the SPIE program, which has been running for about 13 years. And so we have lots of courses, including we have an online course that starts on May 5th. And SPIE Fab is the fabrication prototyping branch. So if you're interested in electron beam lithography, fabrication, or laser integration, or optical fibers, photonic wire bonds, you can get in touch with our program managers and business developers with the contact information provided here. So thank you very much for listening to my presentation.